All right, let's pull back the curtain on the very heart of the internet. Today, we're diving into the TCP/IP Internet Layer. Think of it as the invisible engine that moves, well, everything, from one side of the planet to the other in literally the blink of an eye. This layer is the absolute backbone of our entire digital world.
I mean, have you ever really thought about it? You hit send on something or you load up a website and bam! Information from a server thousands of miles away just appears on your screen. How in the world is that possible? Well, that's the big mystery we're going to solve together right now.
So here's our game plan. First, we'll look at the big picture, the internet's delivery system. Then, we'll zoom in on the digital addresses and packages our data gets stuffed into. After that, we'll follow a packet on its journey, see how it makes that tricky final delivery, and figure out what happens when things go wrong. And finally, we'll tie it all back to how this powers everything you do online.
Okay, Section 1. The easiest way to wrap your head around the internet layer is to just imagine a massive, impossibly fast, global postal service. Its only job is to get digital packages from any point A to any point B, period, no matter where they are in the world.
Now, for all you networking fans out there, you'll know that the internet layer in the everyday TCP IP model lines up perfectly with the network layer. That's layer 3 in the more academic OSI model. Either way you slice it, this is the crucial middleman that stitches all the world's different networks together to form, the internet. So, what does this digital post office actually do all day? Well, its core jobs are what make the internet the internet. It handles logical addressing, giving every device a unique IP address. It manages routing, which is just finding the best path through the maze. It forwards the actual packets, can chop them up into smaller pieces if it needs to, and even handles error messages. It's the master traffic controller for the entire planet.
Okay, so we've got the big picture. Now let's get a little more granular. Just like the real-world mail, every digital package needs two things: a to and from address, and a standard-size box to put it in. This is the basic language of the network.
And that universal addressing system? That's the Internet Protocol, or IP. You could argue it's the most important protocol of the whole system. IP is what gives your computer, your phone, and that server across the ocean its own unique address so they can find each other in a sea of billions of other devices.
And the way these addresses have evolved is pretty wild. The original system, IPv4, gave us about 4.3 billion addresses. Seemed like a lot back then, right? Well, we've basically run out. That's why we have its successor, IPv6. It uses a way bigger 128-bit address, which gives us a number of addresses so huge it's hard to even describe. We're talking trillions upon trillions. Yeah, we're not running out of those anytime soon.
Now here is a really important concept to get. The Internet Protocol itself is what we call best effort. That means it slaps the address on the packet and sends it on its way, but it makes zero guarantees it'll get there, that it'll arrive in the right order, or that it'll be error-free. IP just gives it its best shot. All that reliability stuff, that's the job of the layer above it, the transport layer, specifically the T in TCP.
So this right here is the digital envelope our data travels in, the IP packet. It's got all the essentials for the journey, the from and to addresses, of course, a time to live field, which is super important to stop packets from looping around the internet forever, and a protocol field that tells the destination what's inside. And then the good stuff, the payload, which is the actual piece of your message.
All right, our packet is addressed and sealed. Now for the amazing part. How does it navigate the ridiculously complex web of the internet to find its destination? This, my friends, is the magic of routing.
Routing is basically the internet's GPS. It's the process of picking the best, most efficient path for a packet to take. And this massive job is done by specialized computers called routers. Just think of them as super smart, high-speed sorting offices all over the globe.
But how do routers know where to send anything? Well, they're constantly talking to each other using routing protocols, building and sharing their maps of the internet. And while you might see protocols like OSPF inside a big company's network, the one protocol that runs the entire global internet is BGP, the Border Gateway Protocol. It's the master cartographer for the entire world.
So if routing is about building the map, forwarding is the actual turn-by-turn navigation. Every time a packet hits a router, this four-step dance happens in a flash. The router peeks at the destination IP, quickly checks its routing table for the best way to go, and then zips the packet along to the next hop on its trip. So our packet has crossed oceans and continents, hopping from router to router on the internet's superhighway. But now it has to make what we call the final mile delivery. It's reached the right local network, but it still has to find the one specific device, your laptop, your phone, out of all the others. And this brings up a really cool problem. An IP address gets the packet to your local network, like your home Wi-Fi. But how does it pinpoint your laptop among all the other phones, TVs, and tablets connected to that same router? See, IP addresses are logical. This last step needs a physical hardware address.
For the world of IPv4, the answer is ARP, the Address Resolution Protocol. And it's so simple, it's brilliant. The router basically just yells out to every device on the local network, "Hey, who has this IP address?" The one device with that IP then replies, "Oh, that's me. Here's my physical MAC address," which is like its permanent, unique serial number. And just like that, the packet can be delivered right to it.
And as you'd probably guess, the newer IPv6 has a more modern, more efficient way of doing this. It uses a protocol called Neighbor Discovery, or ND. It does the same job as ARP, but it's just built to be a lot more robust and scalable for the giant networks IPv6 was made for. Now, a packet's journey is not always a smooth ride. It can hit detours, run into errors, or find out it's too big to fit somewhere. So let's look at how the internet layer is designed to handle these common hiccups with some pretty clever built-in tools. First up is something called fragmentation. Imagine you're mailing a really big package, but at some point it has to go through a tiny mail slot. What do? You break it down into smaller boxes. That is exactly what fragmentation is. Every link in a network has a size limit, its maximum transmission unit, or MTU. If a packet is too big, it gets chopped up to fit.
And here again, we see a really smart improvement in IPv6. With the older IPv4, any router along the path could decide to fragment a packet, which can actually slow things down. IPv6 says, nope, routers are not allowed to do that. Instead, the original computer that sent the packet is responsible for making sure it's already the right size for the whole trip. Much more efficient.
So what happens when things just go wrong? That's where ICMP comes in, the Internet Control Message Protocol. Think of it as the network's own built-in diagnostic tool. It's used to send error messages and status updates, kind of like a health report for the network. And the key thing is, it never, ever carries your actual data.
I guarantee you've used ICMP, even if you didn't know it. Ever use the ping command to see if a website is online? That's ICMP. The traceroute command, that awesome tool that shows you the exact router-by-router path your data is taking? Also ICMP. It's the thing that tells you a destination is unreachable and helps manage network traffic jams. It is absolutely essential. Okay, we've gone through a lot of the technical stuff. So now let's zoom back out and see how this invisible engine is powering pretty much everything you do online, every single day. So, why should you care about any of this IP addresses, routing, packets? Well, the answer is pretty simple, because this layer is the foundation of your entire digital life. Every single one of these things, visiting a website, watching a video, sending an email, playing a game, using a VPN, even just connecting to Wi-Fi, is completely dependent on the addressing, routing, and delivery functions of the internet layer. Without it, none of this works.
When you boil it all down, it comes to this. Every single time you click, type, or stream anything, you are creating and receiving IP packets. And every last one of them is addressed, routed, and forwarded by the internet layer. It is the universal, non-negotiable foundation of our connected world.
And that brings us to a final thought. The people who designed the internet built this layer to be incredibly tough, able to route around major problems. But in the world we live in now, with insane demands for speed and new challenges around security, privacy, and the billions of smart devices coming online, what new pressures will this foundational layer face, and how is it going to have to evolve to meet them? Something to think about. Thanks for tuning in.